Okay, so here, now, now let's say we have not biased this. If I didn't bias this, then IB current is zero. IB current is zero. IC current is also zero. Therefore, there won't be potential difference. When there is no potential difference, this voltage has to be 5. Is that idea clear? Now I have not biased this, okay? No biasing. So it is at 0 volt. Now I gave a AC signal just like this. In this AC signal, when we have this positive signal or the positive half, the IB current will increase. The IB current will increase. When this IB current increases, we can observe that uh, this one can go below 5 volt. This one can go below 5 volt. But the remaining half, the remaining half, or let's say it is slightly biased. Okay, it is slightly biased that this part will also uh, yeah, this part is not biased. So will I get this part is not biased? Therefore, will I get this output? This part won't appear here. Okay, clear with that? This positive part will appear here, but the negative part won't appear here. Clear with that? Now let's say uh, we have biased. Okay, we have biased. So this voltage is 0. Give me a minute. Okay, so here, let's say now we have biased this. We have biased using a voltage where the current IB is maximum. Okay, we have a high IB current. For that high IB current, I will have IC current that is almost saturated current. Okay, for that saturated current, this voltage will go for its minimum value, 0 volt. Okay, it will go for its minimum value. Now, let's apply a signal like this. Okay, now remember this voltage is 0. For this bias voltage, this voltage is 0. Okay, have that idea. Uh, now I apply a signal, a AC signal, plus and minus. When we have a positive signal, this voltage has to decrease. But can it go below 0? It cannot go below 0. Therefore, it will remain at 0. And when we have this negative half, here the voltage has to increase. Now it can increase. Okay. So, is the idea clear? When you have 5 volts, that means if you do not bias, some part of the output is getting cut. And when it is biased, so we have the least voltage here, then also some part will get uh, distort. Okay, it is altered. So which will be the best value to set here? Which will be the best value set here? It will be 2.5. According to this, it is going to be 2.5. Why 2.5? Now the voltage is at the center. So when we get a positive signal, it can go up to 0. It can go up to 0. And when we have a negative voltage, it can rise up to 5. That's the best value we can have for VC, right? When biasing. Did you get that idea? So that point is what we call as the Q point. Here, Q point is half the value of VCC. Okay. Here, why this should be VCC by 2? Already the hand is raised, right? So now raise the hand. So let's say the voltage VCE versus time. When VCE is greater than VCC by 2 during bias, okay? When VCE is greater than VCC by 2. During that, our voltage, what was the problem we had when VCE is greater than VCC by 2? The positive half, when we have to increase the voltage, it will get cut. So here we give an input signal like this. This is the input. In this input, initial positive will come below, so it can appear completely, but when it goes to the positive side, it will get distorted. Okay, this is VCC. And when when VCE is less than VCC by 2 during bias, during that, the bottom will get distorted, but the above will appear completely. And when it is equal to VCC by 2, now we can get the maximum. I mean maximum graph without getting distorted. So VCE is equal to VCC by 2 during bias. So this graph will be the best graph we can obtain. Oh, sorry, it's the opposite direction, right? Okay. Uh, Noted all three graphs. To avoid distorted waves, VCE is taken as half of VCC. Half of VCC before introducing the signal. Once you have completed, And now here we used uh, several capacitors, right? C1, C2, C3 capacitors. Now let's look at the purpose of those capacitors. Have you noted before going down? Okay, so note number 3. So this is the uh, RC capacitor. This is resistor RE. This is RB and this is R. C1, C2, and C3. In the previous diagram, I think we didn't have this resistor. It is not an issue, right? You know what is the reason. Can bias by bias resistor, base resistor biasing, or also by potential divider biasing. Here, let's look at potential divider biasing. Okay. Now, can you all remember that capacitor has a special character? In a capacitor, if you send DC voltage, if we have a DC voltage source, for example, battery, when it is completely charged, once it is completely charged, there is no current flow. Current flow becomes zero. And if we have a AC source, if we have an AC source, this AC source, the direction of current will be changing with time. It will be changing with time. Therefore, this capacitor won't get fully charged. Hence, it will allow the current to flow through that. Okay, that property is important. A capacitor will block DC current but allow AC current. This is Earth. So the first point, a capacitor allows AC current or AC current but blocks DC current, Okay, a capacitor allows AC current but blocks DC current. Now, Uh, why do we need to block the DC current? You will understand the purpose clearly. Look, when we apply a signal, when we apply a signal, uh, the current. Now let's say we don't have this capacitor over here. If this capacitor is not present, just like this, right? It is a short circuit path. The current that we obtain from the, why do we obtain current from this source? We obtain that current from the source to forward bias this, or to bias the transistor. But if this path is also available, if this path is also available for current flow, the voltage over here will drop. The voltage here will drop below 0.7. So it won't serve the purpose. It won't serve the purpose. So we have to somehow block the DC current. We have to block the DC current going into this signal, into this input signal. But at the same time, we need to get the input signal to this point. We have to block the current going out, but we have to get the AC signal in. That is why we are using this capacitor, because the capacitor will do both. It will block it will block DC and allow AC. So did you get the idea why we use the capacitor C1? And the same purpose for capacitor C2. In case of C2, the current might go out, right? The current might go out through the output signal, DC current. We have to avoid DC current going to the output. We only need the AC signal going out of the output. To do the job, we need a capacitor, just like this input capacitor C1. Okay, clear with the uses of capacitor C1 and C2. Already hands are raised, so I don't know. Now let me know. So let's write the capacitor C1. The capacitor C1 is to block the DC current, to block the DC current IB entering into the input circuit, into the input circuit. But allow the AC input. Like the remaining also. C2 is to allow the DC current, is to block the DC current IC getting into the output circuit, but allow the AC current. Capacitor C3 is the bypassing capacitor. Copy that. I will explain what is this purpose. Okay. And here we have this resistor R to maintain the current here. Once you have noted all of them, let me know. So here, this C3 capacitor, we call it as the bypassing capacitor, that is to support the uh, working of transistor. The reason is, now when current is continuously flowing through this transistor, what will happen is this transistor gets heated up. When this is heated up, more number of electrons and holes will be formed. Therefore, the current will start to increase. Now, when we have a capacitor, when we have this capacitor, uh, when it is charged, it will maintain a maximum voltage across this resistor. So, which will block the increasing of current. Okay, it will block the increasing of current. So, the current cannot increase, then the number of holes and electrons won't further increase. Okay, it won't further increase exponentially, because when there is chance for the current to increase, then more electrons and hole will produce. That means again current will increase further, then again more electron and hole. So this uh, transistor will get spoiled quickly. Because of this capacitor, it is avoided. You don't need to know in deep how it all happens, but if you have that idea, it's more than enough. Okay. And R and RB is also the same. If we compare, the two types of biasing, we had two types of biasing, right? Uh, Potential divider biasing and base resistor biasing. In base resistor biasing, we will face the same problem I mentioned now. With time, when this heats up, more current will start to flow. Therefore, all the current will try to go through this. Okay, more current will flow through this. Therefore, more IB current. That means again it tries to increase the number of electron and hole. Again IB increases, therefore the current will slowly start to increase exponentially. But when we have a potential divider, this voltage is fixed. This voltage cannot change. Therefore, it limits, or it fixes the value of IB current. Okay, that is why here in this note we have mentioned having this resistor R is better. Clear with that idea, right? Let's see note number 3, note number 4. Note number 4. Now we know what is bias, what are the regions in a transistor. We know the 3 regions in a transistor. By comparing the voltage at collector, emitter, and base, we must be able to identify whether it is in the active region or cutoff region or the saturation region. Now here, if you can remember, we had when this one was forward biased, when VBE is forward biased and this is reverse bias, then only it was in the active region. Okay with that? So to forward bias this region, VB has to be greater than VE. To reverse bias, this, now this is a NPN. So N has to have more potential. That means VC is greater than VB. So if this condition is satisfied, it is in the active mode. Did you get the idea? Or shall I repeat this part? I hope you're okay with this. I hope you're okay with VB has to be greater than VE. Are you okay with VC has to be greater than VB to be in active? Okay, here, first of all, let me know for active mode, we should have VBE region forward biased and VBC region reverse biased. Is that clear? Is that part clear? To have active mode. Okay. Now, this is okay, right? VB is greater than VBE. By looking forward bias, VB has to be greater than VE. That is okay. Now let's look to have reverse bias. To have reverse bias condition, what you have to do for the transistor, sorry, for the diode, for the PN junction, for the P region, we will connect the negative terminal. And for the N region, we will connect the positive terminal. Okay. That means for the N region, the voltage has to be high. And for the P region, voltage has to be low. Then only it is reverse biased. So this condition has to be satisfied. Okay, both of you. Okay. Now let's look to have cutoff region. Cutoff mode. If this is not forward biased, then it is in the cutoff, right? So this has to be reverse bias, no doubt with that. If this is not forward biased, that means if it is reverse biased or it is not biased, in that situation, it is in the cutoff mode. So VBE is less than VE and VC greater than VB. Hope these 2 points are clear. Cutoff mode, is it clear? Sajay, did you get the idea for cutoff mode? Now let's look for saturated mode. For saturated mode. For saturated mode, now from active mode only we are going to the saturated mode, right? So this is anyhow forward bias, then only the current will flow. Now what happens is, this is forward biased. When we are going towards the saturation, VC is decreasing. VC decreases. At a certain instant, it goes below VB. It goes below VB. Okay. If it goes below VB, now it becomes forward biased. So both the side is forward biased. We know how a transistor works. The transistor, one of them has to be forward biased, the other one has to be reverse biased. Then only it will be in the active mode. If both of them get forward biased, current will start to easily flow. After that, there won't be any variation. By varying IB, we cannot vary anything. So both of them get forward biased. If both of them are forward biased, now this is NPN transistor. That's important. So how to make this one forward biased? VB has to be greater than VC. VB is greater than VE. VB greater than VE. And VB is greater than VC also. VB greater than VC also. Okay, clear with those 2 points? Uh, when you are doing questions, in the past paper or anything, when they say it is in the saturated mode, when it is in the saturated mode, you can consider VCE is equal to 0, okay? Almost equal to 0. Because in this graph, can you remember the output graph? Here, look, this value, this is the saturation point, okay? During that time, we will have a value for VC, okay? We will have a value for VC, but that is very close to 0. So you can make the assumption that VCE is equal to 0 and do the question. Fifth one. During saturation, VCE is almost equal to 0 and IC is less than beta times IB. Okay, those 2 points are important. So in a question, they ask, prove this transistor is in saturation. So what you can do is you can find what is beta times IB, and they will give the current IC anyhow. So you will compare these two. If this is greater than IC, then it is in saturation. Okay. How to get this idea? Can you remember the transfer characteristic? The transfer characteristic, we had a graph like this. In this, uh, for IB value, we have the IC value. So in this region, both of them are linear. So for this value, you can find the IC value by multiplying it by beta. But in the saturation, if you multiply it by beta, you will get this value. But the IC value is actually over here. Therefore, beta times IB is greater than IC, right? Is that idea clear? Okay. So with that, we are finishing off BJT part. Next, we have to start FET. Before that, in your past papers, in the page book and in the past paper, we have to try some questions. Once I'll copy, let me know. So that's all for today. You all free on Saturday? If you are free on Saturday, we can start unit 10 and finish it off parallelly. You'll mention that you're not available on Saturday sometimes. So most of them are free in the morning. How about you are free in the morning?